So as stated last week, we are moving out of, well, zooming out of the atomic structure, and now you're looking at diodes and circuits built with diodes, okay? So SCP imagers, again, most of the circuits or systems that you work with are on the data collection signal processing side, not so much into circuit analysis, right? But we will still do a few techniques where you can quickly analyze circuits based on some models. So semiconductor devices like diodes and transistors, unlike a resistor or a capacitor or a inductor, cannot be fully described by just one single equivalent model. Okay, so depending on our application, depending on our need, we can use several different models to analyze these devices. So we're going to look at a couple of these at the top. All right. Okay, so we're going to look at diode circuits and applications of diodes. One application as a OR and AND gate, another application as a diode rectifier circuit, wave shaping circuits, and then you've already applied diodes in the lab for lab 1 and lab 2. So those are the other applications. So the diode characteristics, typical diode characteristics look like this. In the forward bias, you're applying a positive voltage, positive diode voltage to the anode with reference to the cathode. Okay, and we call that as forward bias because it's the forward mode of operation. Simply stated, if you wish to analyze a diode, the anode voltage must be greater than the cathode voltage, or must be higher than the cathode. Okay, if both are at the same voltage, the diode is off. The single criteria for a diode to turn on in the forward region is that the anode should be at a higher potential than the cathode. And then, of course, there's also the diode voltage drop in there. But again, the single most important criteria is that the anode must be at a higher level. So when we plot this in the first quadrant and we say that a diode voltage is positive, what we are saying is that the anode is at a higher potential. So of course, unlike a resistor, there is a small portion of the diode where it doesn't turn on, it doesn't conduct current at all. So it's 0. We've all looked in chapter 1, we saw why that is. And then it rises slowly as the diode voltage is progressively increased. After a certain point, the voltage is sufficient enough to overcome the built-in junction potential. And from that point on, the diode starts conducting. So that's the linear region right there. Okay. So again, non-linear device. So the voltage that is applied to the diode must be greater than the diode built-in potential VBI. Okay, VBI, the built-in junction potential. For silicon, that junction potential is 0.6 to 0.7 volts. For germanium, it's 0.2 to 0.3 volts. Schottky diodes, like the ones we use in the lab, they're approximately 0.2 to 0.3 volts. So that's forward bias. In reverse bias, the exact opposite happens. We are now working in the reverse mode of operation. So the anode is held as a lower potential versus the cathode. Okay, so in this case, the cathode is at a higher potential. So this is forward bias. And in reverse bias, the cathode is at a higher potential than the anode. Essentially, the diode is off. Okay, so if the diode voltage VD is positive and is sufficient enough to overcome the junction barrier potential, then the diode is on and it's forward bias. For all other values, the diode is off. Okay, so if VD is equal to 0, diode is off. It's not conducting anything. If VD is negative, meaning less than 0, again, the diode is off. It's not conducting anything. Okay, And so that's the plot in the third quadrant. Essentially, the only current that flows in reverse bias is due to the minority charge carriers. If you recall from last class, the minority charge carriers on either side, on P and N side, are free to cross across the junction. Okay, so when they're free to cross across the junction, a very small amount of current flows through, representing the movement of those charge carriers. And this small amount of current is known as the saturation current because it increases and it saturates very quickly at a level. That level is typically on the order of like nanoamps and even picoamps. So it's very, very small. Okay, and it remains constant for every particular temperature. It depends on, of course, the dimensions of the physical geometry of the diode, physical structure, as well as the dopant impurity atoms that are introduced into the material. So diodes can handle large amounts of voltage in reverse bias. Okay, that's one of the criteria for operation of a diode. We wouldn't be able to use diodes in any kind of circuit if we would not be able to go more than like 5 or 10 volts in reverse bias. A typical silicon diode, like the 1N series, 1N4000 series, it goes from 1N4001 to 1N4007. These are diode model numbers. Used diodes before this class, right? Or have you? You did? Maybe, maybe not. All right, so 1N4000 series can handle up to 50 volts in reverse bias. And it goes all the way up to 1N4007. And 1N4007 can handle up to 400 volts. You could potentially stick this in the wall and have a rectified output of 120 volts DC. But of course, we don't want to do that. So in reverse bias, for us to actually use them in circuits. So there are a few parameters that we look at for the diodes. Again, remember I said diodes, transistors, FETs, MOSFETs, they're all complicated devices. So there is no single model that can describe their operation. So if you wish to simulate, if you wish to calculate theoretical calculations or perform computer simulations using software like like SPICE, we need to provide as many values as possible about the different parameters of a diode, right? So in just a short while that we have covered the diodes, we have learned that the diodes have built-in junction potential, right? And that depends on the doping and the material that is being used. So if you wish to perform a calculation or a simulation, we need to supply that information. So PSpice has some specific parameters that it uses for diodes. I won't cover everything, but I'll point out the most important ones. Saturation current, IS, is one of the most important ones. That is part of the diode equation. It's part of the Shockley equation, right? So IS is specified by the manufacturer in the data sheet. So you obtain it from there. Series resistance. Transit time. Transit time is basically related to how fast the charge carriers are moving. So how long it takes for the charge carrier to move. CGO, CG stands for the junction capacitance. So junction capacitance quantity comes into the picture because of the space charge region. The space charge region, which is devoid of all charge carriers, meaning free mobile charge carriers, still has immobile charges on either side of the junction. So there's positive charges on one side and negative charges on the other side, right? Which gives rise to a built-in electric potential. So when you have built-up of charges, of opposite charges on opposite sides of a boundary, we can represent it as a capacitance. Okay, so that space charge region gives rise to opposing charges, and it's modeled as a capacitance. So the property of a capacitor is to store electric charges opposite polarity on either side of its plates. So the junction of a diode has capacitance. And that's what CJ stands for, junction capacitance of a diode. And then there are other parameters in there. Talk about all of those. For the most part, we would specify IS, RS, and maybe junction capacitance, and would perform our simulations, and it would be just fine for most circuits. And obviously, if you're performing some higher level analysis, then you'd want to give as much input values as possible. Does that make sense? Right? The more quantities we specify, the more accurate our prediction would be. Okay, but for most part, if all we want to do is get an approximate answer, then we just specify 3 or 4 values and we run with it. Okay. So normal normal semiconductor diodes are represented by this symbol right there. If we operate a diode in reverse bias, at a certain point, exceeding all the the potential in the reverse bias for a diode, a phenomenon occurs. That phenomenon is known as junction breakdown. Okay, and it begins conducting heavily in the reverse direction. And that is noted by this number right there. Okay. So here we see some slope. In real life, there are some diodes that are fabricated specially to work in the reverse bias, and they hold the voltage across the diode at a near constant level. And those diodes are known as Zener diodes, which is shown right here too. So if there are whiskers on the cathode terminal, that diode represents a Zener diode, Z-E-N-E-R. These diodes are specially fabricated to operate in the reverse bias. Okay. In the reverse bias region, breakdown occurs. Let's call it the breakdown region. And this breakdown can occur due to 2 different phenomena. First one is Zener. The second one is known as avalanche. Okay. Zener effect typically takes place around 5.6 volts or less. The avalanche is an effect that takes place higher than 5.6 volts in general. But over the past over decades, it has commonly been known as just Zener. Okay. So if a diode operates in reverse bias, they're just termed as Zener diodes or Zener effect. Even though technically speaking, it would be avalanche effect. And I will explain both. Again, there are some diodes that are specifically operated in reverse bias. They are known as Zener diodes. The special property about the Zener diode is that it will hold the voltage at a near constant level while increasing the current that is flowing through it. Okay, and we'll use this property as a voltage regulator later on. You will learn about in this chapter. Okay, so the slope that you see right here, this slope is actually steep. This is exaggerated. The slope is steep. It's near vertical. If it's near vertical, what you're seeing is the current is increasing and the voltage remains near constant. So the Zener diode has a property of holding the voltage across it at a very constant level. Okay. So these are the two mechanisms, but they both refer to the same thing. So far, so good. There's a lot of information. All right, now let's talk about the two mechanisms, Zener and avalanche. Zener mechanism occurs specifically due to the heavy doping that is done to the p-n junctions. Okay, so for Zener breakdown to occur, there must be a huge number or high number of charge carriers than in a regular silicon diode. And so when you apply reverse bias, it does not take much energy for the minority carriers to actually cross over the junction. Okay, the sheer number of dopant atoms cause a large number of electrons and holes to appear in that p-n junction diode. When you apply reverse bias to such a diode, those large number of carriers will correspond to breakdown typically occurs 5.6 volts or less. Avalanche breakdown, well, it'll say, not say, avalanche breakdown occurs because of the high electric field that is applied in reverse bias. So think about what's happening. We are increasing the voltage. So diode voltage is increasing. 10 volts, 20 volts, 30 volts, 40 volts. The junction barrier keeps on increasing. But at some point, the electric field that is applied to that junction is such a high value that it starts ripping out electrons from their lattice structure. So remember, electrons were intrinsically generated due to thermal energy. Now they are being generated due to the applied electric field. Okay, so a very high electric field is applied when we talk about applying like 10 volts, 20 volts to a few microns of semiconductor material. The applied electric field, the charge density is very huge, and that energy rips out because the energy is being applied in reverse bias. These electrons and these holes are now accelerated through the junction. Process. They're accelerated across the junction. But now, because of the sheer volume of these charge carriers, they're moving randomly and haphazardly. As they move, they're going to collide with other atoms, and this causes more electrons to come free. Those free electrons in turn will collide with more atoms. Again, few more electrons come free. So there's a cascading effect that occurs. The cascading effect occurs very quickly, and it results in an avalanche of free carriers that just tunnel through the junction, hence the name avalanche. Okay. The process is known as impact ionization. So the electrons but regardless of what process is occurring, whether it's Zener, whether it's avalanche, all of those diodes are referred to as Zener diodes. We can buy Zener diodes off the shelf, ranging all the way down to like 3 volts, or I've seen some specific diodes even at like 2 volts. I've personally never used anything that low. The lowest value Zener diode I've used is about 5 volts. Okay. In the lab also, I think you have something on that order. So Zener diodes, again, can range from 3 volts or less, all the way up to tens of volts, like 40, 50, 60 volts. So that's Zener diodes. And then the diode that we've already used for lab 1 and lab 2, the Schottky diode. If the whiskers on the cathode move inward, then it represents a Schottky diode. A Schottky diode is like any other diode, except that one end of the material is not semiconductor, it's actually metal. So you have a semiconductor joined with a metal material. And what this does is it results in a junction barrier potential of around 0.2 volts or less. So the BAT54 diode that we used, or the BAT813, I don't know which ones they supplied, but those Schottky diodes have a junction potential of about 0.2 to 0.3 volts, very small. Okay, and so that's one of the advantages. They have the junction potential is low, plus they perform at a higher speed than regular silicon diodes. So those are the Schottky diodes. And then this one is a varactor diode. A varactor diode, as you see here, has a capacitance represented at one end, which is basically the end of the cathode. So if you see a capacitance symbol at the cathode end of a diode, that represents a varactor diode. The property of a varactor diode is that you can control the capacitance by the input voltage that is being applied. Okay, and there are specific applications for these varactor diodes and Schottky diodes. Okay, in SPICE, compare the values of the saturation current for all these 4 different types of diodes. Then look at the junction capacitance between the standard diode and a varactor diode. Standard diode junction capacitance in picofarads, 4 picofarads, so less than 10. And a varactor diode is about 150 or 150 picofarads. Okay, so that's just typical voltage at a manufacturer specified applied voltage. If we change the voltage, we can change the capacitance. Essentially, we are changing the amount of charge that appears across that junction. All right. And then I want to wrap up with the next slide, which shows some SPICE testing results of the 1N 914 diode. So if you model, if you model the 1N 914, you provide some input from the manufacturer's data sheet, and you run a simulation in reverse bias, the LT SPICE model will show that it does not break down at all. Okay, it will show that it does not break down. So it's not able to capture the finite reverse breakdown of a 1N 914 diode. And you can perform this simulation by yourself, but just input the same values that you see here. You can just pull it in from the LT SPICE model set and run a quick simulation in reverse bias, and you will observe that it does not break down. What you will see is, you will see a constant value of the current. Okay, you'll see a constant value of the current. You're just modeling this in reverse bias. We can see it. So let me add diode this way. And then, of course, this is the power supply. Okay. Simply applying positive to the cathode. So it's reverse bias, but when LT SPICE plots it, thinks it's applying a positive voltage. So which is being shown as the third quadrant is now being shown as the first quadrant. But it's negative voltage and negative current. Okay. The graph is just flipped. One interesting thing I'd like to point out is, we are almost out of time. This additional step right here, dot step in SPICE, you can impart multiple steps to any quantity. So in this case, you are stepping the temperature. If you step the temperature, and in this simulation, you're stepping it from 26 to 28 degrees C in steps of 1 volt each. So it runs a simulation for 26, 27, and 28 degrees. And for a diode, that is very linear. It's a well-established, well-studied fact that semiconductor is temperature dependent. And for a diode, friction is highly temperature dependent and it's linear in relationship. As the temperature increases, the diode voltage and the diode current change accordingly, and the change is highly linear. The single most common application of this is in digital thermometers. If you've used a digital thermometer, like cheap ones, expensive ones, there are two diodes in there, and the two diodes, well, there's a circuit in there. I can show the circuit outside of class if anyone is interested. But you create a circuit using two diodes, measures the reference temperature, and as the temperature changes, the diode voltage changes. And again, because the relationship is very linear and very and fixed, you can calculate the temperature. I mean, you can calculate the temperature as a function of the voltage. Right. All right, so we'll end class here today. We'll pick up here on Wednesday with the applications of diodes using a large signal model.